All right, good morning, everybody. Somehow I'm running late. I don't know how that happened. I came over here early. You all doing all right? You all ready for the test? On Thursday? Okay. How are y'all feeling about it? Are y'all really nervous about it? You feel okay? Did y'all look at the review? Everyone did the review over the weekend? So a little bit of information for you in terms of my office. I get to my office at 7:30 usually, sometimes a little earlier, but my office hours officially start at 7:45. I'm usually there before anybody else is there. And so if you come to my office in the morning, the person in the front may not know I'm there because they got there after I got there. And I usually sit in my office with the lights off. And there's a sign on my door that says if the lights are off, I might be here still, so knock on the door. So I had a student come this morning, and I guess they were told that I wasn't there. So in the future, if something like that happens, you can just tell them, hey, can we double check? Or my cell phone number is on the syllabus, right? So you can just text me, be like, hey, I'm here. Are you here? All right? That way I feel terrible that someone was there and I wasn't able to help them because they didn't know I was there. So, okay. All right. So let's see here. Let's see if that fires up here. Well, that doesn't look good. Oh. Come on. You can do it. What the hell? Try it again. It's like it wants to, there it goes. Okay. All right, so what are we doing today? We are going to do 3.4. So today, finish 3.4. Remember, this material will not be on the exam, right? And we may start 3.5. And then I'm going to stop maybe, 20 minutes early? How much time do we want to save to talk about the exam? 30 minutes? Okay, so y'all have to stop me, okay? So at 10:10 a.m., we'll start doing a review. But please stop me, okay? Because I'll just keep going. So we'll talk about the review at that point. And then, of course, next class is the exam. So for the exam, this is on Thursday. You're going to have the exam 1, right? First one. And I'm going to be nice on this first one, and I'm going to allow you to have a reference sheet for it, okay? So you're allowed one 8.5 inch by 11 inch sheet of paper. That's a standard sheet of paper, okay? And on that standard sheet of paper, you may write formulas, steps, little reminders of how to do things. You may not have worked out problems on that. Okay, so it's not like you're just going to take the review and work out all the problems and then call that your reference sheet, all right? Nothing worked out. Is that clear? Front and back, okay, you can type it up if you want. If you want to like copy paste stuff out of the ebook, you can do that. I don't care. Just front and back is it. Okay, one single sheet. Sound good? Okay. I will check these, so after I pass out the test, I'll walk around. I'll just make sure that, nobody has anything they're not supposed to. If you have something you're not supposed to, I'm just going to take it from you, and then you'll have nothing. So when you're making it, be cautious, all right? If you're not sure, don't put it there, all right?
What would constitute something that you would take away?
a worked out problem. You know, like you worked out a problem. Now, if you write down steps on how to do something, that's okay. Like, for example, how to solve radical equations, right? You could write down, isolate the radical, you know, square both sides, blah, blah, blah. You could write those steps, that's fine. You just couldn't actually have an example worked out next to it.
So you can't have a visual, but you can have it written.
You can have visuals of boxes and arrows and shit that doesn't make sense to me, you know, that makes sense to you. You just can't just work a problem out. Yes? Well, formulas are okay. I'm not sure what you mean by formula.
Well, like, I guess, like, for example, the exponent rules.
Yeah, you can have all the rules.
Okay, just
Yeah.
as long as not it's like an actual example.
Yeah, like, I mean, you could have like x to the n to the m equals x to the n times m. That's fine, right? But you would want to avoid x to the third squared equals x to the sixth because that's a specific example, right? Now, I probably wouldn't care too much for something like this. What I don't want is someone just to come in here with the review worked out. That's what I don't want, right? So, okay, let's get down to what we're going to do here to start, 3.4 and 3.5. If you recall what we were doing last time, 3.4, we had these functions which I talked about like a toolbox, right? These things that everyone here should know, you know, these basic functions that when you see them, you're not like, oh, I have no idea what that looks like. You should know kind of what they look like. And I went through the ones I did last class. So last time, and I'm not going to go through these again, I'm just going to remind you what we did. Last time we had f of x equals a constant, f of x equals x, f of x equals x squared, and f of x equals x cubed. These are I believe, the only 4 functions we looked at last time. And we talked about, you know, what they look like, whether or not, you know, what the domain and range is. We talked about whether or not they were increasing, decreasing, and all that, right? So we're going to continue that now. And so the next one we're going to look at, and let me get to my notes here. The next one we're going to look at, did we do square root? I don't think we did square root. We did do square root? Where did we stop? We did square root? Oh, you did. We did 6 of them.
I think we started cube root. Yeah.
Okay, hold on. We had square root, yes?
Yeah.
Okay, and cube root?
Yeah.
Okay, yeah, y'all are right. So we did those 6. Yeah? Okay. Then now we will continue. The next one that we're going to do here is f of x equals 1 over x. And this is called the reciprocal function. And it's called the reciprocal function because whatever you plug in, it gives you the reciprocal of it. All right? This is one of the most important functions in calculus to understand because the behavior of this function is kind of like at the heart of what you're trying to understand in a calculus class. So let me first show you what the graph of this looks like. And I'm going to do something different for this one than I didn't do this with the previous ones. I'm actually going to draw this function by making a t-table. And we're going to plug in some values of x, and we're going to see what happens, right? So right away, can you look at that right now and tell me what value you cannot plug in? You can't plug in 0, right? If I try and plug 0 into this, 1 divided by 0 is 1 divided by 0 is 1 divided by 0 is undefined, right? What that tells me is that in my picture, I have a problem at 0, right? I cannot plug 0 in. So there should be no graph here. When I look up and down at 0, there should be nothing. Agreed? In all of the ones we looked at last time, none of these had problems at 0. This one had problems with negative numbers, right? But it didn't have any. Everything else had, you could plug 0 into all of these. So we actually have a place where we're undefined here. Let's just plug in some other numbers. How about at 1? Well, 1 over 1 is 1, right? Right? We plug in 2, you get 1 over 2 is a half. Plug in 3, 1 over 3 is a third, right? So let me try and start plotting these points. If I plug in 1, I get 1. I plug in 2, I get 1/2. Plug in 3, I get 1/3. Do you see that these are getting smaller and smaller and smaller? Right? The further I go out, the closer and closer this gets to 0, doesn't it? So if I went out to 10, this would be 1/10. So way out here at 10, it's like really close to the x-axis, right? Will I ever actually touch the x-axis? No, I will never touch, right? Even if I went out to 1,000,000, right? 1/1,000,000 would be some tiny little infinitesimally small number, right? So we are approaching, right, this graph, if you connect these together, this graph approaches the x-axis and never gets there. So the way that we symbolize that idea of getting closer without ever touching is we will draw a dotted, I'm going to do it in red. It's not part of the graph, okay? This isn't officially part of the graph, but I'm going to draw a dotted line along the x-axis. And the idea here is that this graph gets closer and closer and closer. And this is called a horizontal, because it's horizontal. It's called a horizontal asymptote. Asymptote, all right? A horizontal asymptote. So the horizontal asymptote, the way that I think about it is that this horizontal asymptote is kind of like a magnet, right? And what it does is it pulls your function towards it. The further you go out, the closer and closer you actually get, all right? All right, that's what's happening there. Let's continue the t-table. Let's do some negative numbers. So if I plug in -1, I get 1/-1, which is -1, right? If I plug in -2, what do I get? -1/2. Plug in -3, we get -1/3. And isn't it the same sort of thing happening here? Except our answers are negative instead of positive, right? So when we plug in -1, we get -1. We're here. We plug in -2, we're here. And then -3 here, and then we have that same sort of behavior happening here like this. And you can see the horizontal asymptote there as well. So far okay?
Would they go up and down too?
Yeah, so now what we need to resolve is what's happening in here. We know that at 0 it's undefined, right? But what's happening in, like, as you get closer? Because I can pick some numbers here closer to 0, right? Like 1/2. I could do like 1/3, 1/4, 1/5, 1/6. So let's try some of those. So let's start with 1/2. If I plug in 1/2, what's 1/2? 2, right? The reciprocal. You flip the fraction, this is 2. So at 1/2, which is here, I'm up 2. What about at 1/3? 1/3 is 3, right? Flipping the fraction. So at 1/3, which is about here, I'm up here at 3. What would I be at 1/4? 4. 1/5? 5. 1/10? 10, right? 1/100th? 100. 1/1000th? Right? 1,000. Am I ever going to run out of numbers? No, remember, there's no number right next to 0, right? So I could do 1/1000th, 1/10,000th, 1/1,000,000th, 1/1000,000,000th, 1/1,000,000,000th, right? And keep doing that. And I'll do the reciprocal, just keep growing. So we have this behavior here where it goes and it gets bigger and bigger. But remember, it never touches the y-axis, right? We never have a value at 0. So I draw a dotted line this way. And my graph goes, as I approach 0, right, from this side, as I approach 0, my graph takes off to what? What's up there? Infinity, right? I go to infinity. I mean, infinity is an idea, right? I just keep growing, growing and growing and growing. What if I change these to negatives, like -1/2, -1/3? Negative, negative, right? So it's the same thing on the other side except negative numbers, and they're getting bigger. Bigger but negative. So it goes like this. So I have this dotted line here as well that I never actually get to. And this is called the vertical asymptote. We are going to study this a lot more when we get into what are called rational functions later. And we're going to have functions that have multiple vertical asymptotes. And so we're going to have to figure out how what these things look like. It's all based upon this basic picture, though. Okay, that good? All right, now some tricky things. What's the domain of this? What's the domain of this function f? So do I have graph over here? Yes, forever? Yes? Do I have graph that way forever? Do I have everything in the middle? No, what am I missing? At 0, right? So to say that domain, we say negative infinity to 0, don't include 0, right? Union, everything from 0 on to infinity. So it's everything to the left of 0, we've got picture. Everything to the right of 0, we've got picture. But at 0, we don't have any picture, right? How about range? Do we have stuff down here? How far down? Forever, right? All the way up? So do we ever get 0 out of this function? Does this graph ever touch the x-axis? No. So we've got stuff all the way from negative infinity up to 0. Not at 0, though. And then as soon as you get past 0, we've got picture, right? All the way up. So isn't it look exactly the same? The range looks exactly the same as this. Any questions?
It's odd.
Okay, even or odd. So if you take this and reflect this over and reflect it down, right, it's the same graph. So this would be an odd function. Because it's a double reflection. What else? How about increasing and decreasing? This one will be good. Tell me where this function is going up. So remember how we talk about increasing, decreasing? It's as you like go from left to right. If you were like walking along this function, are you ever going to be going up? So over here you'd be going down, wouldn't you? Come down, 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 down. Oh, whoa. Okay, and then once you can't be there at 0, right? So now kind of jump over and stand here and keep walking. We're going what? Down, 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 right? So are we ever going up, ever? No. So we would say this never happens, right? How do we say this never happens? Well, let me do this. Before I answer that, let me ask you this. When is it going down? When are you going down? Yeah, everywhere, right? Everywhere on the domain, right? You can't say it's 0. So you have to say everything over here you're going down, everything over here. So won't that match exactly with the domain? So you're going down everywhere, right? Everywhere that the function is defined, you're going down. How do we say, I guess what I'm trying to get at is, do you all know how to tell me, like these are intervals, right? These are intervals which are like sets of numbers, right? How do you say the set that has nothing in it? Do y'all know how? Have y'all ever seen this before? That right there? This right here is called the empty set. Do not confuse that with the number 0. So for those of you who may have some military background, the number 0 in the military, we put a line through it in the military so that you can distinguish it from the letter O. Do y'all know that or no? Any military? Okay. But in mathematics, this is not the number 0. It's the set of nothing. So a way you can think about it is like, think about you have like this bucket, right? And if I put some things in this bucket, like let me say I put the number 1 in here, and maybe I put the number 2 in here, I put the number 3 in here, then you would say that this bucket is the set of numbers 1, 2, 3, right? Those 3 numbers are in this bucket. I could also put the number 0 in there. Let me take that out. Okay, now let me just put the number 0 in here. So what number is in there? 0, so that would be the set 0, right? What's in the bucket? The number 0. Now, if I tell you there's the bucket and there's nothing in it, how do I represent that? This symbol right here. So that represents an empty bucket as opposed to the number 0, which is something different, right?
Isn't that also the diameter symbol?
The diameter symbol? Diameter of a circle?
Yeah.
I've never seen that as a symbol. Diameter would be like that. I don't know. I've never seen the symbol for diameter, so.
Because I know for like engineering, we do this line straight
Yeah, there might be some notation for that. This is very specific, though, that it's at a slight angle. I don't know if that's the way it is. Is it? Yeah. I'd have to look that up. I've not heard that before. So.
Representation of a German word. I forgot what the word is.
Okay, so that's that function. We good? We're going to move on. The next function we need to know is the absolute value function. And this function is very simple to teach. You can teach this to a very young child, what this function does, right? All it does is just spits out the positive of whatever you plug in, right? So if I sit there and I plug in 1, it's going to spit out 1. If you plug in 2, it's going to spit out 2. But if you plug in -1, it spits out +1. Plug in -2, it spits out +2. So it always just gives you the positive of what's there, right? Everyone clear on that, right? Yeah, yeah? Pardon?
So what's the delta?
Yeah, so we'll get to that. What I want you to do here is, even though you may look at that and be like, yes, I know what the absolute value function is, it's simple. This is actually our first example of what's called a piecewise function, all right? And piecewise functions are a headache for most students, all right, because they're a little bit weird. This is our first example of one. And so what I'm going to do is I'm going to redefine this function. Instead of using the absolute value bars, which you all understand what that means, right? Yes, you all know what that means? I'm going to define it a different way. And it's going to give you the same result as that, okay? So here's the way I'm going to define it. I'm going to write f of x equals, and then I'm going to write a brace like this. And up here I'm going to write x, comma, if x is greater than or equal to 0, and then -x if x is less than 0. Okay, this is an example of a piecewise function. How do you spell piece? Not like peace, but like piece as a piece of pie. P-I-E. Piecewise function. See, again, that one follows the rule. I before E, except after C. So this one does follow the rule, but the word there doesn't, right? Okay, that's a piecewise function. All right, this is our first example of a piecewise function. The reason we call it piecewise is because there's multiple pieces to this function. Right here, okay, right here is the first piece, and here's the second piece. And what this is giving me is instructions on what to do when I plug in an x. So for example, if I ask us right now, what is f of 4? Well, we all know the answer, right? What should happen if we plug 4 into this? It should spit out 4. Okay, so let's look at these instructions. What you do in a piecewise function is you look at the number here, 4, and first you check here and here to see which of these is true. Okay, so look at the number 4, right? 4 is our x. Is 4 bigger than or equal to 0? Yes, right? So what is this telling us to do? Spit out. Well, 4 is bigger than 0, right? So we're going to spit out the 4 that we just plugged in, right? 4. Now, if I plug in -4, what I do is I plug in -4. Now, is -4 bigger than or equal to 0? No. Is -4 less than or equal to, sorry, just less than 0. Is -4 less than 0? Yes. So what am I going to do? The negative of that number. So I'm going to do the negative of that number, -4, and that gives me +4. See, this is saying if you plug a negative number in, you're going to take the opposite of that negative number, which will spit out the positive. Does that kind of make sense?
What would be wrong if that said equal to 0? It's negative.
You could have it here or here, but in this particular problem, it wouldn't matter if you put equals on both, because they have the same value at 0, right? You all good? Yes.
It would always come out positive.
Yeah, do you see that? Because do you agree that if x is bigger than or equal to 0, it's going to be a positive number? Unless it's 0. So this is saying if you plug in a positive number, just give me that positive number as your answer. Do you agree that saying x is less than 0 means it's a negative number? This is saying if this x is a negative number, you're going to take the opposite of that number. and the opposite of a negative would be positive. Okay? So you see how this is always going to spit out the positive? This absolute value function is actually this function. In reality, that's what it is. I mean, I know it's easy to explain what that is, you know, and you don't really need this, but this is your first example of something called piecewise functions. And we're going to, by the end of this section, have to graph some piecewise functions that are not this, that are more complicated, all right?
Question.
Yes?
Is it possible for both of these conditions to be conditions in a piecewise function to be false?
Yes, you could have something where then it would just be outside the domain. So like if this said x had to be greater than 0, maybe this said x is only less than 0 and -3, something like that. Right? If I did that, then that would mean if I try and plug in -4, this is not defined.
So it wouldn't be defined if both conditions are false.
That's right. It wouldn't be defined there. Exactly. Okay. Y'all good? Y'all good? Yes.
Function's like a v, right?
Yeah, so now let's talk about what it looks like, okay? Let's talk about what this function looks like. Well, again, you may know this function from the past, right? But I want us to think about it in terms of these two pieces, instead of like things that you've seen in the past. Okay, do you recognize that function right there? Yes, from last class, right? That was called the identity. And do you remember what it looked like? The perfect diagonal line, right? This is saying that this function we're trying to graph will look like that perfect diagonal line, but only from if x is 0 and on to the right, right? That means I want to draw that picture from 0. What happens if I plug 0 into this? You get 0, right? And then to the right, it should look like that perfect diagonal. And again, it kind of makes sense. If you plug in 1, absolute value of 1 should be 1. You plug in 2, the absolute value of 2 should be 2, right? So on and so forth. Now, this is going back to like the past. The reason we got x here to look like that is because we talked about the slope was 1, right? Last class we said the slope was 1. This is a line as well, isn't it? Where the slope is what? -1. And that means it should be pitched downward, yes? But it should still be a perfect diagonal. So what I want to do is graph that line, but only, let me erase that, because only when x is less than 0. So that means over here, I want to draw this, okay? Which should look like a line coming down like this. Now, I don't continue it through, right? Because I'm only going to go until I get to x is 0. So let me draw it this way. Goes like that, goes up. Now, in terms of this piece right here, in terms of that, at 0, is it defined? No, it's not defined at 0, right? So technically, the red piece should have an open circle there. But the blue piece fills in that circle. Do you see that? So the absolute value function looks like a V. It's a hard V. This is a sharp corner, right? There's no curve to that. It's not like this parabola, x squared, that U shape. It's not that, right? It's a hard V. Questions? Okay. Next one. My screen already turned off? What the hell? All right, the next function, and this is, I believe, going to be our last one. I'll have to double check, but I believe it is. Pardon? Oh, we didn't do domain and range. I'll put it back up there, sorry. Domain and range. So for this, all right, what's the domain of this? Everything, right? Negative infinity to infinity. The range, yeah, you only get output where? From 0 up, right? Do I include 0?
Yes.
Yes? Is it even or odd? Even, right? It's a reflection over the y-axis. You reflect it over the y-axis, so it's even. How about where it's increasing and decreasing? Let's see. It does go up, doesn't it? From 0 on. From 0 to the right, it goes up. So 0 to infinity. And I told you on increasing and decreasing, just always use open intervals, right? And then it's decreasing from negative infinity to 0. That means like, this way, the whole way, it's equal going down. All right.
You only use brackets for range domain.
Yeah, well, I'll say it this way. For increasing and decreasing, just always use parentheses. Brackets, it depends on what you're doing. All right. All right, the next one, the next function, let me tell you what it's called first. It's called the greatest integer function. All right, computer science majors? Computer science? A little bit, few computer science. Okay, this function along with another one is used a lot in computer science, all right? So let me explain what this function is. I'm going to put the definition of it up here. It's a weird function because it's actually a function that doesn't have an algebraic definition. It just has a definition using words. Okay, so this function, which we symbolize with int, int x, is the symbol we use for it. What is it? It is the greatest, I can't spell greatest integer, I can't spell. The greatest integer what?
Greatest integer
Less than or equal to x. All right, so before we can define this function, before we can define it, we need to understand what an integer is. What's up?
What's the thing on top of the eggs? Is that an
Where?
asterisk?
This is an asterisk. There's a note on the bottom that it's referring to. I can scroll down and show you that, but for now, just yeah, it's not a special symbol for this. Okay, we need to know what an integer is first. So the integers, if you look at a number line, the integers are 0, 1, 2, 3, and then forever, right? And then the other direction, -1, -2. So it's the integers are all the positive and negative whole numbers along with 0.